Добрый день, уважаемые коллеги. Сегодня у нас очередной семинар Katherin Shtejer Diaz в связи с избранием на должность старшего научного сотрудника о возможности оценки поляризации пучка по инклюзивному рождению π-нулей в электромагнитном калориметре детектора SPD. Доклад у нас на английском. Вопросы на каком лучше тебе? Ну, то есть вопрос, на каком получится. Тогда все, вперед. 40 минут.
Hello, dear colleagues. I will present a feasibility study. What? Sorry? Микрофон is working. Работает? Да? Да.
Вы сядете подальше, там лучше. Ну, акустика в зале плохая, поэтому дальше вот лучше слышно, чем на микрофон есть. Да? Все на микрофоне есть.
I intend to present a feasibility study and precision estimates for online polarimetry in the ICAL NCAPs of SPD. The first part of the presentation will be dedicated to the analysis with inclusive pi0. And the second part, which is a consequence of the first one, is dedicated to the analysis with single inclusive clusters in the NCAP of ICAL. So SPD, in this project, many spin-related processes will be studied. So the online polarimetry is very important because we need to keep track of the level of polarization in the crossing point of colliding beams with independence of the major polarimeters in NICA. This can give rise to systematic errors due to polarization variations during the measurements of the asymmetries. So the transverse single spin asymmetry will be used to measure the transverse polarization. And the transverse single spin asymmetry can be is defined in this way, as you can see here, which is the ratio of the difference to the sum of differential cross sections with opposite transverse polarization. This transverse single spin asymmetry, which will be used in SPD to measure transverse polarization. I have to say that this has to do with transverse polarized beams and with non-polarized beams. It depends on the polarization and on the azimuthal angle. To get rid of this dependence, we can use the azimuthal modulation form to describe the differential cross-section of a process, which depends also of the polarization and on the azimuthal angle. And we have here in the amplitude, in the modulation amplitude parameter, we have the transverse asymmetry that describes the process, of the process. So initially, the PQCD expectations suggested a suppression of the transverse asymmetry. And some experiments already in last century showed non-negligible values of asymmetries at large X Feynmans at values larger than 0.3 of X Feynman. So this apparent contradiction gave rise to some approaches like the Siever effects, the Collin effects, the collinear twist-free mechanisms in order to explain these asymmetries. Here we have some reference of these measurements well, here, of this measurement with inclusive charged pions and neutral pions. So the measurements of the experiment of the collaboration E704 and collaboration E581 are shown here on the left. We can see here in red and in blue the results for charged pions, which have different signs because of related with the valence quartz fragmented into the pions. And we have the values of asymmetry corresponding to the inclusive pi 0, which are the half of the charged pions, but still they are increasing with increasing X-Feynman that makes them a good candidate for our studies. Our objective is to predict the relative error to which we can measure the polarization if we use the NCAT of the ECAL for online polarimetry in SPG. In the right panel, we can see a compilation of measurements with inclusive pi 0, the measurements of the asymmetries in forward regions, all these experiments, and different collision energies. As we can see, there is almost no dependence with the collision energies, which is a good sign for us. And here, there are the transverse momentum cut values used in these experiments. Well, this is a schema of SPG where is shown the three subsystems that are candidate to be to participate in the online polarimetry. There are the beam counters for measuring the transverse single spin asymmetry for charged tracks, the 0-degree calorimeters for very forward neutrons, and the end cap of the ECAL for the inclusive pi 0. So the pi 0 have advantages that makes them a good candidate because apart from the high cross-section of the inclusive pi 0 production, the relatively easy reconstruction of the pi 0 through the decay of the pairs of photons makes it a very good candidate, and also because the visible asymmetry is not affected by the magnetic field. But we have a big challenge, and there is only one measurement experimental in the energies in which SPD is interested. And these measurements carry with him at very, very high levels of statistical uncertainties. So for our study with inclusive pi 0, we make a simulation with real reconstruction using SPDRoot. With this version, we generated almost 100 million events, was configured for minimum bias. In this case, the elastic collision were turned off, and this was taken into account there in the reaction ratio measurement in order to scale the time to which corresponds our simulated sample. And the reconstruction of pi 0 was through the invariant mass spectrum from pairs of photon candidates. We assume photon candidates like the ECAL and CAP clusters. Some kinematic cuts were applied. The threshold energy of 40 MeV is just to get rid of the contribution of from charged tracks. The PT at 0.5 GeV is just to have some kind of consistency with the kinematical cuts applied in the experiments. And the distribution of invariant mass were fitted using a Gaussian for the signal and a second-degree polynomial for the background. For this analysis, we proposed two methods. The first method, we directly access to the cosine modulation function of the efficiency-corrected pi 0 signal. And once we have the cosine modulation functions in different X-Feynman intervals, we have access to the parameter corresponding to the modulation amplitude, which is what we call here B, which is the product of the polarization and the transverse asymmetry. And in the second method, we don't use the cosine modulation. In the second method, we just take into account that to the signal asymmetry is contributing, to the raw asymmetry is contributing the asymmetry from the signal and the asymmetry from the background. We have two contributions, and we separately estimate this B parameter, which is the let's say, the background asymmetry and the total asymmetry with both contributions, and with them and the ratio of the background to the total contributions, we can access to the signal asymmetry and then to the statistical uncertainty. So this is done for each X Feynman. For each X Feynman, and then once we have this product, we can make just a propagation of errors. We have the term corresponding to the transverse analysis here, transverse symmetry here. As we don't have simulated event, we don't have polarized events, we won't have any asymmetry, so we need to take the values of asymmetry from the experiment, which their correspondent uncertainties. And as for the B parameter, we extract the statistical uncertainties from our analysis, and the B is just replaced, we propose to replace with the nominal polarization of 0.7 that we will have in NICA if we assume small degradation of polarization and so on, and to take the value of the experimental transverse symmetry corresponding to that X Feynman. So we average these relative errors of the polarization with the inverse variance weight, and we will have the final result of the predicted statistical uncertainty for the polarization. So, wait, I think, yes, I skipped this in some moment and I was lost. So at this moment, when not still in details, I was explaining about the first method, I wanted to say that for both methods, the polarization is determined in independent X Feynman beams. We took the same X Feynman intervals that were in the publication of the experiments. We just neglected any change of the polarization during the measurements, and the uncertainties were estimated for the simulated sample, assuming the asymptotic behavior of the uncertainty. We are able to scale to different times of data taking. So as I understood, I already talked about the details of the first method, and here I am showing one azimuthal sector, the invariant mass spectra for different X Feynman intervals with the respective fit functions to the background to extract the signal of pi0. And if you pay attention, in the last X Feynman interval, we don't have here any pi0 signal. And this doesn't mean that we don't have any pi0 contribution. This just means that we don't have access to the pi0 contribution through the invariant mass spectra, because at this energy already the clusters of photons already merged. So it's the first limitation that we have faced during the analysis with this method. So we can work here with these two X Feynman intervals, which is in the ones we have values of transverse symmetry different from 0. So these are the azimuthal modulation functions. They are flat as expected because we don't have any polarization in our simulation, and they were fitted with the cosine function, from where we can extract the parameter corresponding to the modulation amplitude to have access to the polarization, the uncertainties of the polarization. So how reliable is to extract the statistical uncertainty of the amplitude modulation of a flat distribution? This is something that we studied with a simple Monte Carlo, when was generated two distributions, one uniformly distributed and the other one azimuthal cosine modulated. Both were fitted with the cosine functions, and from them we extracted this parameter corresponding to the amplitude. And if you see here a modulation size of 0.5, this corresponds to the highest transverse symmetry obtained in the experiment. We have a difference of only 10%, which is within the tolerable range for this study. So going in front with the first method, at the end we averaged for all interval of experiments, statistically combined the relative uncertainties for depolarization, and we got the final results, which is here, is for the simulated sample of almost 1 minute, 41%. So this means that we will have 10% of error depolarization in 60 minutes. This, of course, is not a good result, but we understand already to which limitations we are facing our analysis. So we went in front with the second method. In this second method, as I have said, so the plane, the circular plane corresponding to the NCAP was divided in 5 beams, azimuthal beams, like in the previous method, but in this case, we work with pairs of opposite azimuthal beams. So we will have 4 pair beams to work, to apply this method, in which we start from the azimuthal modulation form of the differential cross-section, integrate this form, and we obtain the parameter B directly, which is described here for 4 pairs of azimuthal beams. From here, of course, we can estimate the statistical uncertainty of the parameter B for these 4 pairs of opposite azimuthal beams. We do this for the background, and we do this for the total asymmetry, which comprise the contribution of the background and the signal. I have to say that usually in this kind of experiments in COMPASS and in STAR, the background is taken from the side bands away from the pi zero peak, the pi zero signal. But our invariant mass distribution not allows us to have this sideband in one side. So we decided to take just the contribution. This is not a picture for us. This is from start timing, I think. Just below the peak in the region, in the signal region of the pi zero. So in the same way, so we have this asymmetry with the background contribution and with the total contribution and the ratio of the background to the total in such a way that we have the signal asymmetry described in this parameter B, from which we can obtain the statistical uncertainty with this expression. This is done for the 4 opposite azimuthal beams, and this is for each experiment interval, which are then combined in the same way that like in the previous method. So in each method, what we extract differently is the statistical uncertainty of the parameter B. All the rest is contribution from the experimental data. So this is combined, and we get the final result with the method. This is how looks the invariant mass distributions with the second method, and how were defined the regions from which we make the analysis. The overall region under the peak, and just the background under the peak region. Again, we don't have anything at 0.5 of experiments because they are the same invariant mass spectrum. This is only one sector, azimuthal sector, just for illustration. No? And at the end, we obtain this result, which is not very different from the previous one. With the first method, we needed to attain 10% of the relative error of the polarization. We needed 60 minutes, and now we need 40 minutes. This just shows that both methods are consistent between them, but we have exactly the same limitations to use them to predict any error of the polarization on 27 GeV. So we did the same analysis with 10 GeV in SPDRoot. In this case, just was another simulation, but almost everything was the same, except that here was included the elastic collision and properly taken into account just to the calculation of the reaction rate. And this is how it looks, the invariant mass spectrum. This is for the first method, the fittings for the first method. As we can see, this is absolutely different picture because we don't have the merging of the clusters at these energies, and we have a very clear signal even at high X-Feynman. We even can work with 4 intervals of X-Feynman, these the last ones, which are very useful for statistical analysis. These are the azimuthal modulations. And this is for the second method. Pay attention that the very low contribution of the background at these X-Feynman intervals. And the results with 10 GeV are this one, completely different. So we need 2 minutes to attain 10% of relative error of the polarization using the inclusive pi 0 at 10 GeV and from proton-proton at 10 GeV. Both methods are perfectly consistent between them, so the method works, but are not useful for us to predict the error at 27 GeV. So at this moment we can extract some important conclusions. Is the consistency between both methods of analysis. At 27 GeV we don't have good results. The good thing, that means the high cross-section of inclusive pi 0 is very limited by the merging of clusters at X-Feynman equal to 0.5. And at 10 GeV we have much better results. We obtain acceptable levels of relative error of the polarization, and we understand that we need still to predict what we have. We want at 27 GeV, and for that we need to increase the statistical sample. For proton-proton at 27 GeV. So it appeared the idea, thanks to the experience of Alexei Guskov and Igor Denisenko and Amaresh, that it's crucial for the online polarimetry to increase the statistical sample. And for that, we decided to study all inclusive single clusters in the InCAD of ICAL, coming from these proton-proton collisions. So this is the second part of the seminar then. So this should be done at the generator level. That's why a pure Monte Carlo was done with PISIA. We respected all the same kinematic codes in these simulations. The vertex was assumed at the origin and smeared in the same way as before, and it was as it was done with SPDRoot. Photons here were propagated from one of the ECAP, as we can see here illustratively, respecting the distance of this circular plane that represents our end cap from the interaction points and the ratios according to what was reported in the TDR of SPG. And the heat position and the energies just smeared according to the position and energy resolutions already studied for the end cap of the ECAL. So the objective in this first moment of this etap was to predict the cluster asymmetries. For that, were obtained the azimuthal angle distributions in 4 intervals of X-Feynmans, starting at 0.5, which we don't have access to the pi 0 with the previous methods at 27 GeV. Every single cluster originating by pi 0 were weighted with a cosine function, keeping the characteristics, the kinematic characteristics of the mother pi 0, and every single cluster coming from sources other than pi 0 just had weight 1 to the histogram of the azimuthal modulation, the azimuthal distribution. Just, of course, this will be already modulated because we are applying the weighting. So for this we had 2 scenarios. The first scenario when all clusters were considered single, and the second scenario where we took into account some geometrical codes to understand when we have possibly merged clusters, if they are separated at less than 10 centimeters. In this case, this is assumed like one entry to the histogram, which is the same pi 0, which its own characteristics, the X-Feynman and everything. This value of asymmetry will be just the asymmetry from the experimental data. And in the very, very large X-Feynman intervals, we will have just the asymmetry from the parametrization of the experimental data. So in the second scenario, we will have merged cluster when it's less than 10 centimeters. We have in the end cap 4 centimeter cell granularity. That's why we decided to put this value. And when they are separated more than 10 centimeters, but they are coming from pi 0, they are considered single, but they are weighting cosine, with a cosine function. And the single photons coming from other sources, not pi 0, just with weight 1. So that way we obtain the azimuthal distributions we are able to fit. And from this fitting, we can extract the parameter corresponding to the modulation amplitude to get access to the asymmetry that we want to extract. So this is for the first scenario, and this is for the second scenario. Just looks very similar, just the entries are different because in one case we consider merged cluster, and in the other case all clusters were just single. So this is how it looks, the separation distribution between these single clusters at different intervals of X-Feynman, starting at 0.5. So the mean separation is no more than 6 centimeters, confirming the high probability of merging that we have at this X-Feynman. This, of course, confirming the limitation that we had with the first two methods. With this method, we were able to extract the asymmetry values for these values of X-Feynmans. In red, we have the scenarios where the cluster merging were considered, and in blue, the scenarios where all clusters were considered single. Of course, they are consistent between them. This is a good thing, but they are separated just when we have almost all clusters merged. One of these scenarios, the blue, consider all clusters like singles. So they are inconsistent also with consistent enough to 10% of difference with the experimental data. So, and now the thing is to predict the relative error of the polarization, and for that we need to understand which is our sample, which are the expected number of events we have for the pi 0 signal, and which is the expected number of events that we have for background of sources not pi 0. So for that we use SPDRoot. And so this is the same values of the extracted asymmetry just in the table. You can see the consistency between both methods and the difference with the data, which are not too high. So we use SPDRoot just to evaluate the purity in these different X-Feynman intervals. We have 25% of purity in almost all intervals, except in the last one when we have more merged clusters. And so with the expected number of signal events, the expected number of background, and this purity and the asymmetry that we extracted, so we are able to generate azimuthal distributions where our expected signal events, which are here defined like A, are randomized with the cosine function, and our expected number of background is just uniformly distributed. So in that, of course, this can be scaled accordingly to the luminosity, and these distributions scaled already to 2 minutes of data taken are shown here. So the same way that we generated the distribution helped us to construct the fitting function in such a way, because we have fixed values that we already know. These are the expected numbers of events. We have the extracted asymmetry from our simulation. So we have a free parameter here that we can extract, which is exactly the polarization, and we can have just the error of this parameter. So from this, combining by all X-Feynman intervals, we arrive to the final results that finally we can predict for 27 GeV a relative error of polarization of 4.7 in 2 minutes, percent in 2 minutes of measuring time. So this was the objective of all of these studies, and these are the conclusions about what I already commented before. So thank you for your attention.
Thank you. Ну, пожалуйста, вопросы. Что, нет вопросов? Не верю.
Yeah, thank you very much for this report. I must say that I'm far away from this domain, so I haven't understood much. That's why I have plenty of questions. But starting from the beginning, for example, in your method, which you described in the first part of the presentation, you included in your error estimation the measurements from a different experiment, if I understood correctly.
From one experiment?
Yes, from one experiment. And you also include the error from this experiment. Well, from my point of view, you could just use a fixed value for your simulation. You do not include the uncertainty from a different experiment. So what is the reason of including this uncertainty from a whatever 704 experiment?
The parameter from which we extract the polarization in order to know the statistical uncertainty is composed, is just the product. So it's where, in anywhere. Okay, no, okay. Okay, here. So it's the product, this parameter from the modulation fitting function is the product of the polarization and the transversal symmetry. So what we need is the polarization and its statistical uncertainty. So this value will depend on B, which is that parameter, and the transverse asymmetry. When we propagate this error, we have these two contributions when we want to obtain the relative error of the polarization. So in this case, we need the values from the experiment, and what we have from our simulation is this.
Sorry, but in this case, you included it not to the statistical uncertainty, but to systematics. So if you want to perform absolute measurement, that's okay. If we do just relative measurement of local polarization, so you really can skip it.
Okay.
Am I correct?
Yes. And I also have a different question related to the second part of the presentation where you described the 10 GeV results. When you show the invariant mass distribution for pi zeros, if you look carefully, there is a kind of distortion in the peak on the right-hand side. So do you understand the reason?
So let's go there, here.
No, not here, but if you continue, there will be distributions. No. Later.
This is 10 GeV?
Yeah. For example, on the right-hand side in the XF 05 to 06 or 06 to 07, there is a distortion in the peak on the right-hand side. So do you understand the reason?
Here?
Yes.
This is how it's just distributed, the invariant mass. We are taking into account all possible pair combinations in the simulation.
No, but for example, you described the method where you cannot really use the side bands to subtract. Well, here, clearly, there is a kind of bias which you introduce if you do not use the side bands.
Yes, that's true. That's true.
Okay. I stop here.
And related question. No, it's not question, it's comment. So, but your method, this method is valid only if your background under the pi zero peak comes from unpolarized sources. If it's somehow polarized, so if some corrections are needed. So did you try to investigate this issue?
No, not yet.
The asymmetry from the side So what is not like
Maybe
well
it's
drawn on
already
this slide?
implicit.
There is a estimate statistics for the background shown under the peak, but in the reality it should be just a sideband. So in this method, the asymmetry is measured separately for sideband and for the signal region, and then just...
But if it's not shown, it means that the statistical uncertainty of sideband subtraction is not taken into account,
it's
right?
taken, it's just not...
It's taken, so it's just not illustrated here.
Very roughly, for the sideband statistics, the amount of the events under the peak was taken. So there was no attempt to precisely define sideband here, but roughly the number of the events in the sideband was taken as the number of events below the peak. So this might be a bit misleading from this figure, from this picture.
Okay, more questions? I have a few. Slide 33. No, previous one.
Ah, yes.
So, how these values were obtained? I mean, if I simply scale this 4.74, so just divide it to square root of 5, I should have 2.12 instead of your 2.23.
No, I have done that, and it's very, very close to the 3% that we have.
But I mean, you
It's like
simulated independently each time.
Independently.
No sense you can just skip.
And I have just anyway. I proved. After that, I just proved that they are consistent and why the square root. Yes.
Okay.
They are very near to this value.
Okay, I understand. So the second question is just a comment. Could you show your cuts?
At the beginning, when the simulation is here.
For instance, this one. What is the sense to apply cut on PT and on the cluster energy? I mean, PT cut includes already this cluster energy above 0.4.
You are asking exactly about the PT, right?
Yes.
As far as I understand,
cut on the PT absolutely includes cut on the cluster energy.
Yes, that's true.
Okay, and one more serious question. But what about negative X Feynman?
In the negative Feynman, I did not study because we wanted just to understand.
Yeah, but you have it.
But yes, but they are like from the experiments like zero. More
no, you see,
if
you emitted negative X Feynman,
yes.
It means that all your numbers are. I mean, it's roughly double your statistics, but mostly unpolarized.
Yes, for
so
this
roughly
study
you
with
should
Pitya,
increase your errors by the factor of square root of 2,
for
right?
the study with Pitya, maybe it is taught, but anyway...
The expected asymmetry for negative X Feynman is either 0 or unknown. There are no results
the asymmetry are 0 for X Feynman
indicating
negative.
notable asymmetry for negative X Feynman.
Yeah, but asymmetry is practically 0, we know it. But the statistics, do you have the events with negative X Feynman?
Yes, but...
In the same encode, I mean...
That's right, but in that case...
I mean, for this direction, negative X Feynman will be exactly in your end cap.
Exactly, yes.
So half of the statistics will be...
This can be done just to test how much this can be improved, yes. But I concentrated the analysis in only one end cap, taking into account how it started this analysis.
But probably you should take it into account. Especially it's interesting when beams have different polarization.
Okay, thanks. It's a good suggestion, but we needed the transverse asymmetry values different from 0 for the first part of our analysis, how it was conceived from the beginning.
But you automatically have these events. And my question, do you take these events into account?
No.
Just statistically?
No, but...
So of course the asymmetry, we can assume that asymmetry is 0. But if now it's not taken into account, so you can double your statistics,
Okay.
but by unpolarized contribution.
Okay.
Okay, more questions, comments? Окей, if not, ну давайте поблагодарим докладчика еще раз.